we'll move on to the next reaction. So the next reaction it will involve the breaking of the CO bond to give you ester and acyl chloride. Now, so this one you should be quite familiar. Carboxylic acid can react with alcohol via a condensation reaction to give you ester. So condensation, the carboxylic acid will contribute the OH, alcohol will contribute the H to give you water. Then you join the C of your carboxylic acid to the O of your alcohol to give you to form the ester bond. Now, this reaction is also a nucleophilic acyl substitution reaction, meaning that it involves the attack by a nucleophile. Now, you need to take note, this carbon here in your carboxylic acid is electron deficient, as I said earlier. So, it will be susceptible to a reaction with a nucleophile. And what is your nucleophile here? My nucleophile is my alcohol because it has a lone pair on that oxygen, which can be donated to this carbon. And when you do so, the CO bond will be broken and you will substitute out the OH group. So this is a simplified mechanism, not the actual mechanism for nucleophilic acyl substitution. So that's why this is called nucleophilic acyl substitution. So a nucleophile attack and substitute out the OH. Now take note, this is a reversible reaction and we need concentrated H2SO4 and heat for the reaction to take place. Why do I need concentrated H2SO4? So you notice that this is equilibrium. Therefore, the U will not be very high. And in order to increase the U, I need H2SO4 to act as a drying agent, which will take away water. So you will shift the position of equilibrium to the right-hand side to produce more water because water is being taken away. So as a result, your ester, the U will increase. Then H2SO4 is also used as a catalyst to speed up the rate of the reaction to establish the equilibrium faster. Okay, but even so, with the catalyst, this is not a good method to prepare your ester because this is reversible, the U is not very high, and therefore usually what I will do is I will change my carboxylic acid to something that's more reactive. So carboxylic acid, you should change it to a acyl chloride, then the reaction will be better. Now then the next thing is we know that alcohol can react with carboxylic acid to give us ester. Now what if you change your alcohol to a phenol? Will the same reaction take place? Because recall, this is formation of ester is a nucleophilic acyl substitution reaction. Your carbon here in your carboxylic acid is electron deficient, and phenol actually has a lone pair of electron which can come in to give that electron deficient carbon and substitute out the OH group. But this donation cannot take place. There's no such reaction at all. Why not? Because phenol as a nucleophile is weaker than your alcohol. Why is phenol a weaker nucleophile than alcohol? Now, because phenol, you must take note, the p orbital on the oxygen can overlap with the pi electron cloud. And because of this overlap, the lone pair of electron on your oxygen is actually delocalized into the benzene ring. So instead of being donated to the carbon, it will go into that benzene ring. And when it's delocalized into the benzene ring, what happened here? It is less available for donation. Okay, so therefore phenol is not nucleophilic enough to react with carboxylic acid. Okay, because the lone pair is now delocalized into the benzene ring. Now then, so phenol is not a good nucleophile, but how come I can still form this type of ester? Because if you look at this ester here, this part here involves a phenol. Therefore, I can still use phenol to form ester. But to form this ester, I cannot use a carboxylic acid because there's no reaction. So instead of using a carboxylic acid, I need to use something that's more reactive, which is the acyl chloride. So I cannot use carboxylic acid. Instead, I need to change the OH to the Cl here, okay, which is more reactive. Then the reaction can take place. So the next part of the reaction we're going to look at is how to convert carboxylic acid to a acyl chloride, because it's an important reagent. So similar to your reaction with alcohol. So alcohol, the OH group can react with PCl5, PCl3 and SOCl2, where the OH will be substituted by the Cl via a nucleophilic substitution reaction. So when you look at carboxylic acid, the same type of reaction can take place using PCl3, PCl5 and SOCl2, where the OH group is substituted with Cl. Okay, so this is also a nucleophilic substitution reaction. And what you need to take note here is that when you use the 3 reagent there, it must be an anhydrous condition. Why anhydrous? We told you before, the 3 reagent can hydrolyze in water. So if you have water, they will react with water and you have no more PCl3, PCl5 and SOCl2 to react with your carboxylic acid. So I cannot have water. And because it's very reactive, this reaction will take place at room temperature. You don't need heat. Now, so what you need to take note, PCl3, PCl5 and SOCl2, you need to know how to write out the equation. So you just replace the OH with Cl. If you use PCl3, it will give you H3PO3. If you use PCl5, it will give you POCl3 and HCl. SOCl2 will give you HCl and SO2. Now what you need to take note, the last two, PCl5 and SOCl2, produces HCl, which are gas. So HCl gas will be seen as white film. So therefore, over here, you can put a star there. This is also a good chemical test to identify carboxylic acid. But you must take note, alcohol can also react in the same way. So if you have alcohol, you cannot use this. But if you have other functional group, you can use this to identify your carboxylic acid. Okay, so this is also a good chemical test. Now, next, we're going to look at another type of reaction that carboxylic acid can undergo. So we know that carboxylic acid is formed from primary alcohol via oxidation reaction. Okay? Now if you want carboxylic acid to give you back your alcohol, the reverse reaction must take place, which is reduction. But now the question here is, what is the reducing agent that I should use here? Now, so this one is not in your, lecture notes. So later on you can take a photo. So now, these are the 3 reducing agents that you are exposed so far. Sodium boron hydride, lithium aluminum hydride, and your hydrogen with the metal catalyst. So now, so we know that sodium boron hydride and your lithium aluminum hydride both only reduces polar bond. So they cannot reduce, so I put a cross, they cannot reduce CC double bond, cannot reduce CC double bond, because CC double bond is not polar. But sodium boron hydride is a weaker reducing agent. Lithium aluminum hydride is a stronger reducing agent. So that means lithium aluminum hydride can reduce more functional group because it is stronger. So sodium boron hydride being weaker and it can only reduce polar bond, so it will only reduce aldehyde and ketone. So aldehyde and ketone has a CO double bond now, which is polar. Okay? But lithium aluminum hydride being more reactive, being stronger, it will reduce carboxylic acid, ester, amide and nitrile as well, because it is stronger. Then how about your last, the hydrogen with nickel and platinum catalyst? Now, this one, they can reduce alkene. This one you should know, CC double bond, aldehyde, ketone, and also nitrile. Okay, so you can take a photo. But over here, what I need you to take note here is that if you need to reduce carboxylic acid and its derivative, which is ester and amide, I can only use lithium aluminum hydride. So if you need to reduce carboxylic acid and its derivative, only lithium aluminum hydride can be used. So therefore, for this part, if you need to reduce carboxylic acid to primary alcohol, we will use lithium aluminum hydride. Okay? Now, take note, how do I balance the equation? we use this square bracket H to balance the hydrogen for reduction reaction. So this was explained to you when we were covering carbonyl compound tutorial lecture. Now, what you need to take note here is that reduction means that there is a decrease in oxidation number. So, which is the element where the oxidation number has changed? It is the carbon, where the oxidation number has changed. Now, next, move on. Now, other than reduction reaction, carboxylic acid can also undergo oxidation. But what you need to take note, there are only 2 carboxylic acid that can be oxidized. The rest of the carboxylic acid cannot be oxidized. So only these 2, methanoic acid and ethane dioic acid. So that's why I asked you to circle ethane dioic acid later, just now. So carboxylic acid cannot be easily oxidized. Therefore, you need stronger oxidizing agent. Because carboxylic acid cannot be easily oxidized, so I use KMnO4. So you cannot use K2Cr2O7. Potassium dichromate cannot oxidize carboxylic acid. Carboxylic acid cannot be easily oxidized. Only these 2 can be oxidized. And you need to oxidize these 2, you need the stronger oxidizing agent. And what do they get oxidized to? Methanoic acid become carbon dioxide. Same thing, ethane dioic acid become carbon dioxide, but you have 2 moles because there are 2 carbon in ethane dioic acid. Okay, Ken? So, this is also a good distinguishing test to check for the presence of these 2 carboxylic acid because they are the only 2 carboxylic acid that can be oxidized. So, you will see purple becoming colorless. So, if you had these 2 carboxylic acid with other carboxylic acid, you can use this as a distinguishing test. Okay? So with that, we have looked at all the reactions that carboxylic acid can undergo. So you need to start to memorize the reagent and condition.